welcome to Mrs. Shin's class. Today we're going to go over maximum and minimum point of a graph. When we differentiate a function, we obtain a gradient function, right? And using that, we are able to find the gradient of the function at any point. So here you go. This is a summary. This part, when you differentiate it and insert a, okay, instead of x, say this part is a, so if I bring it down at this curve, I can find the specific gradient of it when I differentiate the function and insert a. Okay, remember back in linear, okay, if it's going down, we can say the gradient is negative. If it was going up, we could say the gradient is positive. Okay, if you want to find the gradient at this point, what is my gradient at this specific point? It's going up, so it's going positive direction, positive, right? My gradient is still positive, still positive, still positive, right? But when it gets to the horizontal, what happens? My gradient is 0, right? Turning, right? What's my gradient looking like? It's negative back now, negative, negative, and so on. Okay, this value, it's still negative, 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 right? But when it gets here, horizontal, my gradient is 0. Good, right? And back again, positive, positive, right? Okay, so we can add this to our note. At turning point, when it's maximum minimum, the gradient is 0. We call this stationary point. And notation wise, if I differentiate the function, okay, and if it's 0, then it's a stationary point, saying the gradient when is 0, right? Right. Not only the minimum and maximum. Okay, have a look at this. This is neither minimum or maximum, but have a look. At this point, my gradient is going down, negative, 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 and what happens at this point when it becomes horizontal? 0, okay, and then coming back this way and negative. So therefore, there's another stationary point at this one, right? So not only at the local maximum and minimum point, we call this point of inflection, and this can be another stationary point. Like this, okay? So there you go, we can sum up like this. If the function, differentiated function, is greater than 0, then it's positive number, right? The gradient is positive, so the function is increasing. Right, if it's less than 0, obviously it's negative, then it's going down, decreasing. And if the differential function is equal to 0, these are the stationary points. Right, let's have a go at doing this question now. It says find the stationary point of the function below. Okay, right, can you differentiate this straight away? No, so what do you need to do? I need to expand the bracket and simplify. Yep, okay. Right. What do I need to do if I want to find the stationary point? Right, stationary point, remember, the differential equals 0, right? So I need to differentiate this function once, let it equal 0, and find the x value. Okay, this is a differential. And let it equal 0. So let's find x. X value will be 3/2, right? Okay. Now it says stationary point. That means both x and y, the coordinates. So in the original equation, I'm going to insert 3/2 in here. 3/2, 3/2. And calculate the y value according to it. Okay, which is 12.25. So therefore, I can pull it right over here and write down the answer. 12.25. There you go. This will be my final answer. Okay, there you go. This time it's cubic. I want you to find the stationary point. In order to do that, obviously, I'm going to differentiate the function and let it equal 0 to find the x values. Okay, people, this is quadratic equation. So you can either factorize it or put it in the calculator and find out the x values. Okay, if you try factorizing it, this is how you do it, and if you just want to use calculator, that's fine. Okay, how you find it in the calculator is go to equal. My one is number 8. I'm gonna scroll it down to the side. There you go. Right, it's polynomial, my equation. Okay, the highest power is 2, which is 2 over here. Right, my a value is -3. Right, I'm going to press -3, followed by -6 over here. And the last one, 9. Okay, and enter again, enter. Then I'll get my final solution, 1 and -3. Okay. Remember, this is one way to check your answer for quadratic formula. Okay, you should use evidence. You should show and use the evidence of quadratic formula and find out the answer by using calculator. So for this one, I want to find the corresponding y value. In order to do that, in the original equation, I'm going to put 1 and 9 times 1 minus 1 cubed minus 3 times 1 squared minus 5, and I'll get the answer 0, okay, for the corresponding y value. So over here, that will be 1 coordinates of the stationary point. Okay, and if I do -3, then I'll get -32. So therefore, another coordinate will be, there you go, those two other stationary points of the cubic. The next question is asking the nature of these stationary points. So it's asking whether these 2 points are maximum, minimum, or point of inflection. Alright, so 1, 0, -3, -32, those two are stationary points. So it could be, either one of the 3. So therefore, let's figure it out. This is a very important rule to figure out the nature. Okay, I have dash dash, that means second derivative. If my second derivative is negative value, then I know that point is maximum. If the second derivative is positive, I know it's minimum. If it's equal to 0, that's point of inflection. Okay, let's find out how we use this chart. Okay, remember this was f dash function, the gradient function. I'm going to differentiate once again, double dash, looking first differential, second differential. So that one, it's exactly the same. Okay, you see that 9 disappears, 3, 2 comes down, it's -6x minus 6. Okay, so I just differentiated the first one again, second differential. Alright, my first one, x is -3. So if I put -3 into the function, okay, it's -6 times -3 minus 6, which is 12, okay? So this is a positive value. Let's have a look. Okay, double dash. If it's positive value, then I know that the point, this one, will be a minimum. Okay, again, this one is positive. When it's positive, greater than 0, then the point should be minimum. Okay, let's have a go with this point. Right, this time I'm going to put 1 into it, into the second differential. So -6 times 1 minus 6, what would it be? It's -12. So since this value is less than 0, which is looking like this, then it's a maximum. So I know this point should be a maximum. Okay, then let's draw the picture. Remember, this one is local minimum, and the other one is maximum. Yeah? And I'm just going to link it together like this. Okay? People, you need to show this proof of test in order to find out whether it's maximum or minimum. Okay, you need to show this. However, you can check it with the calculator. Okay, the way to check it is go to menu. Okay, go to graph, which is number 3 for mine. Okay, what I entered is the original equation, the cubic fx, right? Fx, I just re-entered it in here. Enter. There you go. Okay, you can see the full graph of the cubic. This at the maximum, this at the minimum. How do I know it's max and min with the exact value? Okay, you go G-solve. Okay, you see maximum over here. 1, 0. Okay. Should we have a go at doing the minimum? The same. There you go, it's finding the value like this. So you can tell using calculator to check, right, whether the point, the nature of the points is maximum, minimum, or inflection point. Now it's asking what values of x is the fx decreasing, right? Remember, this going up is increasing function, going down was a decreasing function. So it's asking decreasing, okay? It's going down. So have a look, which part of the graph is decreasing? This part is going, going down, 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 down. From there to there is decreasing function. Going up, 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 back, down, 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 right? So basically, from -3 down this way, it's all decreasing function. And from up 1 and up this way, it's all decreasing function. The only increasing function in this graph is in between these -3 and 1. So there you go, have a look again. When x is negative, less than -3, for example, -4, 5, 6, the function is decreasing, whereas if the value of x is greater than 1, 2, 3, 4, 5, for example, 2, 3, 4, 5, those functions decrease. Okay, so that will be my final answer. Okay, let's have a go at doing the final question. Right, stationary point, and I pick this time where the function is in fraction. Okay, if you see fraction, then it's really difficult to differentiate it, right? So in this case, I'm going to put it in negative power, like this. Okay, remember stationary points, I have to differentiate it and let it equal 0 because that's what the stationary point is. So I'm going to try differentiating the function. However, this is again product rule. I don't want to use product rule too much because that's going to complicate it more. So I'm just going to expand the bracket because that's a simpler way to do it. In this case, you're adding the power, so 2 minus 1 will be 1. Plus 4x to the power of -1. Now I'm going to differentiate it like this and let it equal 0. Right, since I need to find out the value x, I put 1 to the other side, and should we cancel negative, negative? Okay, and I can just go across multiplication, and my x value will be plus minus 2. Don't forget plus minus. Alright, now I need to check what the corresponding y values are. Okay, when x is 2 and -2, remember to find out the corresponding y value, I'm going to put it in the original equation over here, right? And I'll get my answers like this. Those two will be my stationary point of the curve. Okay, so this is what we have covered together. Maximum minimum point of a gradient. Alright, okay, so this note is very important. Okay, so all these notes, have a reread and please write it down in your theory note. Okay, and have a go at doing the pages from the book. I will see you in the next lesson.